Okay, so today I'll be starting, the first lecture will be about the superparticle, and then in the afternoon we'll do the superstring. So instead of starting with so this was the relativistic particle which gives a scalar. And this one this gives us spin 1/2. We'll see that this one I think there's a half. At least in d equals 10. So this, of course, is in any dimension. This one we're going to restrict to d. So I thought it was turned on. It's turned on here. So probably that's a button there. It might be that it's not closed. I don't know. They say it's quiet. Can you turn up the volume, or maybe the wire's not? So the green light's on, so the battery is working. Is that better? No. Yes? Is that better? It might be the... Hello? 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 Okay. Okay, thanks. Now it's probably too loud. Okay. Is this okay? Okay, thanks. Okay, so we're going to restrict to d equals 10. It turns out the spectrum here, you can also discuss this in other dimensions. But in d equals 10, it describes a super-Yang-Mills multiplet, which has a gluon and a gluino. Before doing this, let me ask if anybody resolved this question here. So the question was, remember in the cohomology we found that if you had p/phi equals 0, so this is a spinor, and p squared phi equals 0. So we had these 4 different cases. So this one's not allowed because this implies this. And we had p squared phi equals 0. And finally, so I was unable to show that this one did not give any cohomology. Did anybody look at this? Did anybody try to look at it? Okay, so it was kind of a trick question because I fooled myself. So there was a mistake I made in the lecture, which is that I said that this one gave the right cohomology. In fact, the right cohomology comes from this one. Okay, so what I showed in the class was that this one gives no cohomology. So let's suppose that p/phi is non-zero and p squared phi is non-zero. Then the question is, does this imply that phi is p of slash of something? So if it is p/ of something, then there's no cohomology. Okay. So in this case, it's easy to see that omega is just p/phi over p squared. Right? Because if you hit this with p/, you get p squared. They're both non-zero, so this makes sense. So this one, no cohomology. Now what I said in class was that this one gave cohomology because I didn't find a solution. But in fact there is a solution. So suppose you write phi is equal p slash h slash phi divided by p dot h. So I assume that p squared phi is 0, but p is not 0. So h is any vector such that h dot p is non-zero. Okay, so if p is non-zero, you can certainly find an h such that h dot p is non-zero. Okay, so let's check that this obviously satisfies p slash phi. So because p squared equals right, because p slash phi equals 0, because p squared equals 0, it's clear that p slash phi equals 0. So let's show that this is equal to phi. Well, because p slash phi is 0, you can pull it through here. So actually there's a 2 here. So this is equal to p slash h slash phi over 2p dot h. Right, because p slash phi is 0. And this is just phi. Okay, so what we've shown is that if p squared phi equals 0 and p slash phi equals 0, then phi is p slash of something. Okay? So there's no cohomology here either. So the cohomology actually comes from here. So here, suppose phi was p slash of something. If phi was p slash of something, then it's clear that p slash of phi is equal to p squared of omega. We're assuming p squared equals 0, so that's 0. So that violates this. So that means if p squared phi equals 0 and p slash phi is not 0, this is impossible. Okay? Yes? Here, this one? So I'm assuming that p squared is diagonalized. So so that means p squared just has eigenvalues. So if phi has eigenvalues of p squared equals 0, then omega will also, because the p squared of course commutes with p slash. So just think of p squared as just some diagonal matrix, which means that if the diagonal matrix acting on this, the diagonal matrix commutes with p slash. Diagonal matrix commutes with everything, but okay, it also commutes with p slash. So that means if I write phi as any matrix acting on omega, it's just going to, I mean, the eigenvalue of p squared here is going to be the same as the eigenvalue of p squared here, just because it commutes with that p slash. So as long as you assume that you can diagonalize p squared, then that's a legal statement. Okay, so what you have shown is that here, in fact, there is cohomology, because what you've shown is that in this case, phi cannot be written as p slash of omega. Okay, so here you get cohomology. So the only states here are the states which cannot be written as p slash of omega. So that means that this gives states in the cohomology. Okay. So in fact, what you would usually call the massless spinor here is not phi, it's p slash of phi. So if I define chi equal p slash of phi, then of course p slash chi equals 0. So this would be the massless spinor. Okay. So in the, remember at ghost number 0, the state was just the phi itself, phi alpha. At ghost number 1 and at other ghost numbers, it's actually p slash of the state, which is the massless spinor. Okay. Okay, so that's how you get this infinite cohomology. It doesn't come from this one. Sorry, it comes from this one here. p slash h slash phi. So what you show is that if p slash phi is 0, it can always be written as p slash of something. Okay, so now we go back to superhanging. Okay, so let me get the factors of I and signs like that, right? So usually you put i's here because remember that the Grassmann coordinates anti-commute. So let me just get the sign. So I think it's minus I in my notes. Okay, so let me put some indices here, and let me, before we go into the analysis of this, let me review what I said earlier about the gamma matrices. So I'll use the same notation as in the notes here. So the capital gamma matrices are 32 by 32. And just like in 4 dimensions, you can write them in a Weyl representation, which will be written in terms of 16 by 16 matrices. And the notation that I'll use, which is convenient notation, is that alpha and beta go from 1 to 16. But remember, a spinor in 10 dimensions can have 32 components. So we'll say that an object with an upper index is Weyl, and an object with a lower index, so for example, this object here will have a lower index, I'll call it anti-Weyl. So remember that a 32 component spinor, you could write it in terms of these plus and minus notation. And let's say theta alpha will be even number of pluses. And this will be an odd number of pluses. So for example, this state minus minus minus, it says 0 pluses, so this would be theta alpha. So minus 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 minus. So these are there's 1 of these, there's 10 of these, and there's 5 of these. These are the 16 components of theta alpha, and the other ones which would be plus. Here you can have 2 minuses, and here you can have 4 minuses. You have 5 of these, and 10 of these, and 1 of these. So this is how the 32 component spinor splits up into Weyl and anti-Weyl. And there was a question yesterday after about how this would look in 4 dimensions. So I think this will be convenient just to, for people that are familiar with 4-dimensional gamma matrices, you can do something similar. So in that case, you have, if you work in 2-component notation, you have theta alpha and theta bar alpha dot. So in 4 dimensions, unlike in 10 dimensions, this is the complex conjugate of this. So this would be Weyl. This would be anti-Weyl. In 10 dimensions, it turns out that the Weyl spinor is already real. So the complex conjugate is still Weyl. But in 4 dimensions, it's anti-Weyl. So this would be plus plus minus minus. This would be plus minus minus plus. And now let's see what the gamma matrices look like in 4 dimensions. So the gamma matrices in 4 dimensions are similar. So they are the forms, let's say, for j equals 1 to 3, it's just the Pauli matrices. And in the 4th direction, or in the 0 direction, this is either 1 or minus 1. So these are 2 by 2 matrices. So let's look at 4 dimensions how this breakup of the gammas is related to this plus plus minus minus. Okay? So to try to reinforce the definitions of this plus plus minus minus. So remember we defined gamma 1 plus I gamma 2, gamma 1 minus I gamma 2, gamma 0 plus gamma 3, and gamma 0 minus gamma 3. So these are the creation and annihilation operators. So this one is going to be equal to, so it's 0 here. And then sigma 1 plus I sigma 2 is going to be 0, I think it's 0, 2, 0. Now on the other side you'll get 0, 0, 2, 0. Right, because you get 0, 1. No, I think it's probably this one. And then on this side, it's going to give you 0, 0, 2. Right? So this is sigma 1 plus I sigma 2. This is sigma 1 minus I sigma 2. Are people following what I'm doing? Okay. Here, you get 0, 0. And now it's you get sigma 0 plus sigma 3. So you get 2, 0, 0, 0. And here there's a minus sign. So you get 0, 0, 0, minus 2. Okay. And finally here you get 0, 0, 0, 2, 0, 0, 0, 0, 2. And here you get 0, no, here you get minus 2, 0, 0, 0. Okay. Okay, so there are my 4 by 4 matrices. Okay. Now you can see precisely which components of theta it annihilates. So let's suppose we're looking at plus plus. That's supposed to be annihilated by this one and by this one. So if I did it right, if you look at this this spinor with 4 components, it's annihilated. If you hit it on it, the only one that's going to survive is 1, 0, 0, 0. Right? Because if it has something in the second column, it won't be annihilated by this. If it has something in the third column, a third row, it won't be annihilated by this, and the fourth row won't be annihilated by this. So this corresponds to the component plus plus. Right? The theta plus plus is this thing here. Right? Because it's annihilated by gamma 1 plus I gamma 2 and by gamma 0 plus gamma 3. Okay, what about minus minus? Somebody wants, so here's the minus. Which one survives the minus? Sorry? The last one. Right. Because the only column which has nothing is the second column. Okay? Okay, what about theta plus minus? So that's annihilated by this one and by this one. Yeah, right. Okay, and the last one is, so we see that the vial components are the first two, and the anti-vial are the second two. Okay, that's why it's called vial representation. So the top half is vial, and the bottom half is anti-vial. So the same thing will happen in 10 dimensions, but instead of being 4 components, you'll have 32, and the top 16 will be the vial, and the bottom 16 will be anti-vial. Okay. Okay, any questions? Yes? Minkowski. So if you don't use Minkowski, if you use Euclidean, then instead of being gamma 0 plus gamma 3, you'd have to do gamma 0 plus I gamma 3. Okay, that's the only difference. Any other questions? Okay, so now we're going to quantize. So from the first exercise, remember, there was something else I forgot to tell you, is that these 16 by 16 matrices are symmetric. So it's similar to like Pauli matrices, except, so if this is in the 0 direction, this is minus this. If it's in the j equals 1 to 9 directions, this is equal to this. Okay, so when we quantize, it looks like you just have this first class constraint, okay, p squared. But there's something funny, because it's not just px dot. P also acts on theta dot, which means there's going to be a canonical momentum for theta. So remember when we wrote the Lambu-Goto action, if you start with this action and then quantize, you define P equal, and then you find that this satisfies certain constraints. Well, this was if we wrote it just in terms of x's. If we write it in terms of x and thetas, we also have a canonical momentum with respect to theta. So the canonical momentum with respect to theta is going to be defined to be small p. It has a lower index because, remember, theta has an upper index, and this is dd theta. So this is the definition of the canonical momentum with respect to dot. So we find that it is equal to minus I pm over 2 gamma m theta. So that means the canonical momentum to theta is related to capital P, the momentum conjugate to x, and theta. This doesn't involve time derivatives. So it's not like P equals x dot. That means that this object here is not independent of the coordinates. So you have a relation between momentum and coordinates, which means there's a constraint. So this is a constraint. The constraint, we use the letter D. So this is the same kind of constraint as p squared constraint. I mean, it comes from, again, from finding that the momentum are not all independent. So if they all depended on time derivatives, then they would be independent. But because they depend on things which are coordinates, the momenta are not independent from the coordinates. Yes? Yes? Vial spinors. So theta alpha is a vial, which means the canonical momentum, which I'm calling P alpha, is anti-vial. Okay, so this is the notation alpha, beta, alpha, beta. So remember that the gamma matrix, these small gammas, have either both up indices or both down indices. The reason is because when you hit with a gamma matrix, it changes a down index into an up index, because it changes vial to antivial or antivial to vial. Just as in 4 dimensions, a gamma matrix changes an alpha to an alpha dot. It changes vial to anti-vial. So and that's why it doesn't have one up and one down. That would preserve if it's vial. Yes?
Why did we construct the action with the vial spinor and not the Direct spinor?
Okay, so the number of thetas you introduce is related to the number of supersymmetries you want to have. So remember the supersymmetries I defined to be delta xm is going to be equal to minus 2. So this is what's called n equals 1, d equals 10 supersymmetry. If you want to introduce more thetas, you can. So for example, if it was a Dirac spinor, that would be like introducing a vial and an anti-vial. That would be called n equals not 1, but n equals 2. So this n describes the minimal number. So n equals 1 would be 16. But if you had n equals 2, you'd have 32 supersymmetries. So you could do it. It would turn out, it wouldn't describe super Yang-Mills anymore. It would describe another theory related to supergravity. Any other questions? Okay, so this is a constraint. Now, as Dirac showed quantization in the presence of constraints, you have to first determine if they're first class or second class. So the way you determine that is by taking the commutator of the constraints and see if you get a constraint or not. Okay, so the constraints we have d alpha, we also have p squared, that's also a constraint. So first of all, d alpha with p squared is 0. That's easy to see because this doesn't have any x dependence, so everything here commutes with capital P. But d alpha does not anti-commute with itself. And the reason is because p alpha with theta beta is not 0. Precisely because this is the canonical momentum. So I'm just trying to remember the factors of I. Otherwise minus I. So I forgot to tell you why there's an I here. There's an I here because you want the action, of course, to be real, or more precisely Hermitian. And theta alpha is Hermitian if you're working in Minkowski space. But when you take the Hermitian conjugate, you flip the order. So theta dot gamma m theta, if you take the Hermitian conjugate, it gives you theta beta gamma m beta alpha theta dot alpha. So I switched the order. This is symmetric, but theta dot anti-commutes with this. So this is equal to minus. So in order to cancel this minus sign, that's why we put the I here. Okay. Yes? It's not 0. We'll see what it is. So I didn't compute it yet. If it was equal to 0, then these would be first class constraints. Okay, so let's compute it. So we have, of course, p alpha with p beta, that's fine. That's 0. And this term with this term is 0. So I get plus. Well, there's no. Okay. But then you get the cross terms. So the cross terms are non-zero. So this term here, because P alpha with theta is non-zero, it's going to give you, okay, minus I times I over 2. So it's going to give you P m over 2 gamma m alpha beta. And this will give you the same thing. Okay, where the contribution comes from here, yes? The same reason as there is in, so I set h bar equal to 1, but yeah, these are Poisson brackets. So, okay, so when I write down these are Poisson brackets. I'm going to do, yes, at least I think so. I haven't read a quantum mechanics book in a long time, but sorry? So he's asking about the I. You're asking about the minus sign? Okay. So I don't remember, but I think it's normally defined with an I, but I might be wrong. I see. Okay. Okay, so then you're right. So there's no I. Take away all the I's. Okay? It doesn't change anything. But as soon as we do this, we're going to quantize, and then you'll have to put the I's back in. Okay? Okay, but nothing will change. I guarantee nothing will change. No, the Dirac brackets will be different. So the Poisson brackets will not be equal to the Dirac brackets because you have second-class constraints. But I'm not worried about the factors of I. They're different. It has nothing to do with the I. The fact that they're different. Okay. So in the notes, I put the I's. So if you like, this is a definition, and it's related to Poisson brackets by a factor of I. Okay. Okay. So that means this is equal to you get 2 factors of a half. So this is equal to Pm gamma m alpha beta. So what we find is that this is not 0. It's related to the momentum, but it's not related to a constraint for the momentum, right? Because Pm is not 0. So that means this has second-class constraints. Okay. Now it turns out to also have some first-class constraints. So the first class constraints you see, because although Pm is not 0, P squared is 0. So P squared is one of the constraints, of course. Now, to see that this has both first and second class constraints, the easiest way to see it is to choose a Lorentz frame. So let's suppose that P plus is the only component which is non-zero. Okay, all the other components are 0. That's what I'm saying. Then it turns out this is just, of course, equal to gamma minus so gamma minus is a null matrix. If you square it, you get 0. And you can show that half of its eigenvalues are 0. So it's a 16 by 16 matrix. But you can show that it has this form, where here this is a 8 by 8 matrix. So this would be gamma minus. So it has 8 components with eigenvalue 1 and 8 components with eigenvalue 0. It's similar to what we did in 4 dimensions. So in 4 dimensions, remember, we were looking at gamma 0 plus, or Pauli 0 plus Pauli 3. That would be the analog in 4 dimensions. And this, remember, was equal to the matrix 2, 0, 0, 0. So this had one component, one eigenvalue non-zero and one eigenvalue 0. But instead of being a 2 by 2 matrix, this is now a 16 by 16 matrix. So it has 8 eigenvalues non-zero and 8 eigenvalues 0. Okay. If you wanted to write gamma plus, just to gamma plus would be 0, 0, 0, 1. Okay, so either one of them kills half of the components. It's just they kill the different half of the components. Okay. Okay, so that means that this matrix has 8 eigenvalues 0. So of course I've assumed that p squared equals 0, because obviously I'm assuming the only non-zero component is in the p plus direction. Yes? So gamma plus is just gamma 0 plus gamma 9. Okay? There's no gamma 5 here. Forget about gamma 5. You can construct a gamma 11, but that's unrelated to this. So gamma 11 would tell you if it was vial or anti-vial, just like gamma 5 tells you if it's vial or anti-vial. But here it's just gamma 0 plus gamma 9. These are all, it's a 16 component, 16 by 16 matrix. So these gammas you should think of as like the Pauli matrices, not like these capital gammas. Okay. Any other questions? So what that means is that this has 8 first class constraints and 8 second class. Because 8 of the components have non-zero eigenvalue, so that means they're just non-zero, and the other 8 are 0 if you assume that p squared equals 0. P plus is p0 plus p9. Okay, any questions? So now we have a new problem that we haven't seen before. Some of these constraints are first class and some are second class. When they're all first class, we've seen this many times. We know what to do. We do BRST quantization. When we have first and second class constraints, life is more complicated. So Dirac gave a procedure for quantizing with second class constraints, which is related to these Dirac brackets. Dirac brackets we can define, but usually they're not very useful. Let me tell you why they're not useful. So the Dirac bracket, if you have 2 operators, so this is for Dirac bracket, it's defined to be the same brackets, Poisson brackets, so everything we had before are just Poisson brackets. But then you have to subtract a term. So let me tell you what these phi's are. So these phi's are the constraints, the second class constraints. And this C is a matrix whose eigenvalue or whose elements are just the commutator of the Poisson bracket commutator of 2 second class constraints. So in our case, phi is just D. Okay, we're doing anti-commutators because they're fermionic, but that's not the point. So these are the 2 second class, so any 2 second class constraints, they won't commute to 0, they'll give you a matrix. And if these are second class, this matrix is invertible. Means it doesn't have any zero eigenvalues. If it had zero eigenvalues, then of course some of these would be first class constraints. So if all of these phis are second class constraints, you define this matrix, and then you define the Dirac bracket in this way. So this is in this little book by Dirac called Lectures on Quantum Mechanics. This has the property that if you take the commutator of anything with a constraint and you do the Dirac bracket, you'll find that it's zero. That's why you subtract off this term. I'm not going to do the computation, but it's trivial. So that's of course important for consistency. You want something if you want to look at on the constrained surface, you want anything which commutes with that constraint, it better still be zero on the constrained surface. Okay, so the problem with Dirac quantization is this is an operator in general. It won't be so of course in this semi-classical approach, this is just a matrix of numbers. But in principle, this could be an operator. And in quantum field theory, we don't know how to invert operators. So this procedure, it's almost useless when you want to discuss quantization. Okay, in this special case, it's even more complicated because part of this matrix is first class and part of this is second class. So we cannot just simply invert this matrix because this matrix has zero eigenvalues. We have to first separate out the first class piece. Okay? The only simple way to do that is to partially gauge fix the theory. So we want to perform a procedure which remove first class constraints the simplest way is to gauge fix. So what does gauge fix mean? So because this involves 8 first class constraints, the first class constraints are related to gauge symmetries. So the fact that we have gauge symmetries here means of course we can do some gauge fixing. So let's figure out what those gauge symmetries are. Okay, and then we're going to gauge fix. So this is the simplest way. So using this procedure, what we're going to do is we're going to figure out the spectrum of this theory and show it describes precisely this d equals 10 super Yang mills. But we're not going to be able to do it in a covariant way. Okay? It's going to break the symmetries down to light cone gauge. And then in the next part of the lecture, we'll see how this can be avoided by working with these pure spinors. Okay, any questions up to now? So half of these d alphas will be second class and half will be first class. If you tell me which direction the momentum is in, I can tell you which half are first class and which half are second class. It turns out that the first class constraints, if I hit it with p slash, these turn out to be first class constraints. And the other ones are second class. Okay. Okay, but the simplest way to proceed now is to look at this action and ask, well, since there are first class constraints, this action should have some symmetries. Okay. In the same way as the Nambu-Goto action has reparameterization symmetries because of the first class constraints. So these symmetries are called Kappa Symmetries, and there are 8 of them precisely because there are 8 first class constraints. So the symmetries were found just by looking at this action. So Siegel was the first one to find it. So the symmetry is of this type. So P slash is of course PM small gamma m. Okay. So this kappa is just some arbitrary Grassmann parameter, which can depend on z, or it can depend on tau. So it's a local symmetry. And then in order to cancel the variation of theta, you have to also transform x. this way. Right, this delta theta is the same as here. You have to transform also, so P is invariant, but you also have to transform E. So the exercise for tomorrow is to show that this is a symmetry of this action. So the action will change up to a surface term. This is a local symmetry. It's called Kappa symmetry. Now it looks like, because kappa is a spinor, so it's vaguely related to, it looks vaguely like space-time supersymmetry, because if epsilon was equal to p slash kappa, this is almost the same thing as, I'm worried about the signs. 1 second. So in the notes, it looks like there's an I that was dropped. Sorry about that. So I'm going to use in chapter 2.1, I dropped the I's in the action, sorry. Okay, sorry. So there's an inconsistency between chapter 1. How did that happen? 1 second. Okay. I'll fix it. Okay, in any case, this has the opposite sign from the Kappa symmetry. The space-time supersymmetry is plus theta gamma delta theta. Here it's minus a half theta gamma delta theta. Yeah? Okay. Okay. Sorry. Now I'm confused what's going on. Okay, so I'm following my notes here. Normally I guarantee all the formulas work with the I or without the I. It's just that you're going to get, always going to get the cancellation. So if I put an I here, obviously I have to put an I here. I can try to do it on the spot. Sorry? Hermitian. Yeah, so that's why, so usually you put an I here. Okay. There's an alternative. So let me tell you the alternative. Since this is the alternative that I'm going to use here. When you define Hermitian conjugation, you don't have to flip or complex conjugation, you don't have to flip the positions of the thetas. So if I define theta 1, theta 2 star to equal theta 1 star, theta 2 star, then there's no need to put an I here. Okay. So in these notes, and Friedan Martinek-Schenker does the same thing. I didn't invent this. In these notes, I'm going to use this convention. Okay. I don't know why I started putting in the I's and then I thought I saw the I's here somewhere, but I guess I was wrong. Okay, so in any case, then there's no I here and there's no I here, and then there won't be any sign errors compared with the notes, I hope. Yeah? For the bosons, changing the order doesn't do anything because they're bosons. So it's only relevant for the fermions. So it's just a definition. It's a convenient definition just because it removes the eyes from the Lagrangian. Okay. Okay, so this is this global symmetry. And this is a local symmetry. So they're different symmetries, and it's good not to confuse them. And they have different signs here. Okay, so they're not. One is not a subset of the other. Okay. Now this local symmetry means that you can. In fact, you have to do gauge fixing in order to define propagators. Okay. So the way I've written. Normally what we have a local symmetry, we gauge fix the Lagrange multiplier. Okay. When we do pure spinors, we'll see that that's essentially what we're doing. But in this case, we don't have any Lagrange multipliers here, so the only thing we can do is you can gauge fix some of these fermions. It's a fermionic symmetry, we have to gauge fix some fermion. So we're going to gauge fix half of the components of theta to be 0. So this symmetry is going to be used to gauge fix gamma plus. So actually this is a done. So remember, gamma plus has only these components non-zero. So it means that the last 8 components of theta are going to be gauged to 0. Okay, so only the first 8 components are non-zero. Good, okay. Very good, thank you. But it's always multiplied by p slash. So what that means is that, remember, p slash is a 16 by 16 matrix, but 8 of the eigenvalues of that matrix are 0. So for example, in this Lorentz frame, only these 8 are non-zero. Yeah. So although it looks like there's 16 gauge symmetries here, it turns out there are only 8. For the same reason that there are only 8 first-class constraints here. So you can only gauge fix 8 of the components of theta to be 0. So this assumes that, I assume p plus is non-zero. If p plus is 0, then you can't do this gauge fixing. So I'm not assuming p plus is the only component non-zero. I'm just assuming that this component of p is non-zero. So here I was assuming that p plus is non-zero and all the other components were 0. I'm just assuming that the plus component of p is non-zero, which is the usual thing when you do light cone gauge fixing. Okay. Okay, so this gauge fixing doesn't involve ghosts because there's no, or the ghosts don't propagate because there's no time derivatives here. So we can just write down what the action looks like in that gauge. Okay. So we have the usual PM xm dot. We still have EP squared. But now this term, of course, you have the term theta dot alpha gamma j, alpha beta theta beta pj. We have the term gamma plus, p plus, let's call it p minus. And then finally we have the term minus. So these are the, I just wrote this in terms of all the different light cone components. Okay. This term is obviously 0 because we gauge fix gamma plus theta equals 0. It turns out this term is also 0. So to show that this term is 0, let's insert gamma plus, gamma minus, plus gamma minus, gamma plus over 2. Right, this is just the identity. Okay. This second term is obviously 0 because gamma plus acting on theta equals 0. This first term is 0 because gamma plus commutes with gamma j, or anti-commutes with gamma j. So this is the first term is equal to theta dot gamma plus gamma j theta. So this is also 0 because gamma plus theta is 0, so gamma plus theta dot is also 0. So this first term also goes away. So we're just left with this term. Okay. Gamma minus is this matrix here. So this just picks out 8 of the components of theta, this term here. So the action just simplifies to theta dot A 1/2. And I'll tell you what I mean by theta dot A. So I've written theta alpha so alpha goes from 1 to 16. I've written it in terms of two 8 component. So A and A dot equals 1 to 8. And of course, these 8 components are annihilated by gamma plus, and these 8 are annihilated by gamma minus. Okay? And I'm using notation A and A dot to distinguish them. Okay? This turns out to be, if you look at SO8 representations, this turns out to be an SO8 vial representation. This is SO8 anti-vial. Okay? Okay, so this is just, there are 8 thetas which survive. Question, yes? This, I'm gauge fixing this local symmetry. Sorry, the symmetry is all of these. So these are how all the fields transform under the same symmetry. You have to transform everything, otherwise the action is not invariant. That's the exercise. So the exercise is show is invariant under this. Okay. The gauge fixing condition is this. So we used this kappa, this transformation here, to gauge fix half of the thetas to 0. So in that gauge, the action simplifies to this action here. Okay, is it clear? It's okay, yes? Yep. Very good. Good question. So when I write gamma plus with down indices, it has this form. But when I write gamma plus with up indices, it turns out to have the opposite form. So gamma, what I'm really computing is this. So this is what I mean by the commutator. And it turns out that gamma plus with with up indices is 1, 0, 0, 0, and gamma minus okay. So the reason why this changes is just like in 4 dimensions, if you remember the gamma j was equal to, these have the same sign if it's from 1 to 9, but it has opposite sign. In the 0 direction. So if you take 1 plus this, 1 plus gamma 9, and they have up indices, it's like then the one, let's say the top half cancels, but if you take it with down indices, you get the opposite sign here. So that's why when you lower or raise the indices here, remember this is with up indices, is with down indices, you flip the sign of one of them, and that's why you flip the sign here. Okay. What? Oh, thank you. Yeah. Thanks. Any other questions? Yes? The Spinor indices? Okay, so it's similar to in so in 4 dimensions, let me give you an analogous thing. So we have gamma m and here I think they're called sigma bar m in Wesson-Bagger. And the only difference is that the sigma 0 is the opposite sign from sigma bar 0. So there's no Lorentz transformation that takes you, I'm not sure what you're asking, there's no Lorentz transformation that takes you from this one to this one. So simply there's no Lorentz transformation that takes you from this to this. So you're not allowed to raise and lower indices of these spinors just because there's no Lorentz transformation that takes you from a vial to an anti-vial representation. So you can take an alpha to an alpha index, but you can't take an alpha into an alpha dot index. So I don't know if that answers your question or if you had a different question. Yeah. Yeah. Good. In 10 dimensions you cannot. Yeah. No. So there's no way to change. There's no Lorentz transformation that relates this to this, for example. In the same sense as in 4 dimensions, there's no Lorentz transformation that takes this Pauli matrix into this one. Okay, so you're right. The notation in 4 dimensions, you're right. The notation is different because the notation in 4 dimensions, instead of having up and down indices, I had alpha and alpha dot. So the analog of going from an up to a down in 4 dimensions is going from an undotted to a dotted. And that you can't do using Lorentz transformation. Okay, any other questions? Okay, so now we have a system which now it's easy to compute the spectrum. So we're finally at the point where we would show that the spectrum is super Yang-Mills. So why can we do things now? Because now the canonical momentum to theta is just theta itself. So these are SO8, A equals 1 to 8. And now there is a metric, so you can raise and lower indices just using delta AB. So these 2 indices are just contracted with an SO8. It's just the identity matrix. So and there's a P plus also. Yes. So we can get rid of these factors here by just defining, let's define SA to be equal square root of P plus let's even put in a 2, I think. I'm not sure about the factors of 2, but maybe I even have a square root of 2 here. I have a 4th root of 2, I'm not sure why, but okay, so that means that this action here is just going to become, I think I'll erase it and you'll see it again later. So the commutation relations for the S's are precisely the same thing you saw before for the psi's in the spinning particle. So SA with SB is just going to be equal to delta AB. Now, before, these were not Spinor indices, these were vector indices. Remember, compare with psi m with psi n is 2 8mn. But other than that, it's the same type of relation. So these you quantize using gamma matrices. And more precisely, capital gamma. And the ground state just had a Spinor index, right? So the way we quantize the system with these psi's is we use the fact that these anti-commutation relations are the same like the gamma matrices. So we can quantize it by just choosing your representation such that psi m acting on this ground state is just equal to gamma m alpha beta acting on the ground state in this way. So that's why the spinning particle gave a massless spin 1/2. Now we have something different just because this has a SO8 spinor index. So we have to know a little bit about gamma matrices in SO8. And it turns out in SO8, so let's say J equals, so A equals 1 to 8. Let's say J equals 1 to 8. So this is a SO8 vector. This is an SO8 chiral spinor. And finally we have an SO8 anti-chiral spinor. And all of these have 8 components. So it turns out that in 8 dimensions, 8 Euclidean dimensions, the gamma matrices are also 8 by 8 matrices. So they satisfy. And just like in 4 dimensions, 4 Minkowski dimensions, they carry their 8 by 8 matrices, carrying one SO8 chiral index and one SO8 anti-chiral index. So let me say more carefully what I mean. So this is a matrix with J equals 1 to 8, A equals 1 to 8, P dot equals 1 to 8. And it satisfies the following property, that if you contract the dotted index and you symmetrize in J and K, you get 2 delta JK delta AC. So you get so first of all, they anti-commute unless J is equal to K. That's what we have here. But this is, of course, the identity matrix. So this is an 8 by 8 identity matrix with just this delta AC. So there's another way to write this, which is instead of contracting the dotted index, you could contract the undotted index, and it turns out to be the same relation. So if I just, instead of contracting the dotted, I contract the undotted, so this would be A C dot, A B dot, A B dot, A C dot. You get the same relations. So I just take the product of two of them, and instead of contracting the dotted, I contract the undotted. There's one more thing you can do, which is instead of contracting the Spinor indices, you could contract the vector indices. This is also true. So I'm going to contract these and symmetrize in the undotted. This is also true. So these relations, it turns out that these three types of SO8 indices are related by triality. So if you look at the Dinkin diagram for SO8, you find that these three appear in a symmetric way. So these matrices also satisfy this triality property. It doesn't matter which of these indices, you contract any two of these indices of the same type, and you symmetrize in any two of the other indices of the same type, and you'll get a relation of this type. Okay. So this is a special property of SO8. Now, because of this property, it's actually simple to quantize this. The only thing you have to remember, these are SO8 Spinor indices. If these were SO8 vector indices, what you'd get is the same thing as we got here. So if these were vector indices, then you'd get a ground state which is a spinor of a Weyl spinor and an anti-Weyl spinor. Just like you got here. Remember, this ground state here has 32 components. 16 would be Weyl and 16 would be anti-Weyl. In this case, if I was doing SO8, you get a spinor where 8 of them are Weyl and 8 of them are anti-Weyl. So that's what you would get if this S was an SO8 vector. In this case, it's an SO8 chiral spinor. It's this. So that means, using this triality, instead of getting A and A dot, you get a vector as an anti-chiral spinor. So this is a vector of SO8, and this is an anti-chiral or anti-Weyl spinor of SO8. So what we found is that when we quantize this system here, the ground state, instead of being a SO10 spinor as we had with the spinning particle, we find that the ground state is an SO8 vector or an SO8 anti-Weyl spinor. Now, of course, you still have this part of the action, so this tells you that p squared equals 0, so everything is massless. And these are just the physical degrees of freedom of super Yang-Mills. So this is the gluon. So if you go to light cone gauge, the gluon is just described by a massless SO8 vector. And there's a massless SO8 spinor, which is the gluino. And they're related, of course, by space-time supersymmetry, because this action, although it doesn't have all the space-time supersymmetries manifest because you've gauge fixed some of the thetas to 0, you can easily show that the action also has space-time supersymmetry. So these two particles, of course, are related by space-time supersymmetry, as they are in super Yang-Mills. Okay, so what we've derived is the spectrum of this superparticle action. So this is super Yang-Mills. But to do it, we have to do it in this non-Lorentz covariant way. Okay. So, question? Yeah. So this index here is a Weyl spinor. Okay. So what we've done, we have a triality between these three. So if it was a SO8 vector, then what we see is it takes SO8 chiral spinor to an SO8 antichiral spinor. So in this case, how does psi j act? Psi j acting on 0a just gives you gamma j, I guess I'm calling it capital J, j a dot 0a dot. Right? Now in this case, how does S act? So SA acting on the vector just gives me gamma j a dot acting on an antichiral spinor. So it changes, it's the one. Okay. Any other question? Okay, so what we found is that the spectrum of this superparticle quantizing in light cone gauge gives you super Yang-Mills. So we'll take a 5-minute break, and then we'll see how pure spinors allows you to do this in a covariant way. Okay, so are there any questions about what I did in the first half? Okay, so now we want to figure out a way to quantize this in a covariant way. So what we're going to do is we're going to add some new degrees of freedom, which will turn out to, at first level, it looks like you're complicating the theory, but in the end, you're going to get a simple covariant version of the theory. So what are the variables we're going to add? So we're going to start from essentially the end point of the Brink-Schwarz superparticle with these degrees of freedom, which is not Lorentz covariant. Okay? But we're going to get to this point by adding some more variables, and then we're going to show that in one gauge, it reproduces this, but in another gauge it reproduces a system which is manifestly Lorentz covariant. And then of course we're going to use the manifestly Lorentz covariant description. Okay, so what are the degrees of freedom we want to add? So we're going to add a new set of thetas. So it looks kind of crazy. So remember, this S came from starting from some thetas and then gauge fixing. We're going to add a new set of thetas, but we're going to add it together with its canonical momentum. So in some sense, you should forget about these thetas. These thetas are unrelated. To this one. Okay? So they're unrelated, more precisely, they're unrelated to S. Okay, they're just independent variables. And now together with that, we're going to add a Lagrange multiplier, which remember was somehow missing in this description. In this description, we had a Lagrange multiplier for this constraint, but we didn't have any Lagrange multiplier for the fermionic constraints. So we're going to add a Lagrange multiplier for the fermionic constraints. But the fermionic constraints cannot be just d alpha. Remember, d alpha is equal to p alpha so this constraint here was second class. So this was d alpha with d beta. It gave you p slash alpha beta. Because we want to do BRST quantization, we want a first class constraint here. Now we're going to construct something which is first class, which looks not very nice, but it will have the property, at least, that it's first class. So we're going to add a term. Instead of just having d alpha, we'll call this object here d hat alpha. Okay. So this d alpha here was originally written in terms of these thetas. Okay. We've already forgotten about those thetas. Those thetas don't exist anymore. So let me just erase this. I defined it in this way, where this is p alpha and this is theta alpha. Okay. So because I defined p alpha, I should have said this: p alpha with theta alpha, with theta beta is just delta alpha beta. That's just, it's no longer Dirac bracket. It's just because in the same way as p and x is delta mn, p and theta is just delta alpha beta. Okay. Yes? Yes. Alpha is 1 to 16. Okay. Yep. That's right. So A is 120. So we've added this first class constraint. So it's first class, as I'll show, because if you compute d hat so first of all, this term commutes with this term because there's nothing, the thetas don't know about the s's, okay? But remember, s has the commutator that s alpha with s beta is equal to gamma minus, actually I think it has a down index, gamma minus alpha beta. This is the same thing as SAB. So this is just written in 16 component notation where half of the components are 0. Okay. Okay, so we can compute now the commutator of this with itself. So you get, of course, the contribution from the first term, but you get another contribution from the anti-commutator of this with itself. So what you'll get is p slash gamma plus, gamma minus, gamma plus, p slash divided by p plus. So you get two factors of 1 over square root of p plus, that gives the 1 over p plus, and you use the commutator of s with s, so that just gives you p slash gamma plus, then you get the gamma minus from the anti-commutator of s with s, and then you get another one of these. Okay. So the claim is that this is equal to this when p squared equals 0. So first of all, gamma plus, gamma minus, gamma plus is the same as gamma plus, so this is equal to p slash gamma plus, p slash over gamma plus, over p plus. And now I anti-commute this, so this is equal to minus gamma plus p squared over p plus, plus the commutator. So the anti-commutator is going to give you plus p slash over p plus. So up to signs and factors of 2. This term here, so sorry, this is, I can't, okay. This p plus, of course, cancels 1 over p plus. So this term here can cancel this. So if I get the signs right, this is probably minus, and this is plus. So in the end, you just get p squared over p plus times gamma plus alpha beta. So we find that d alpha with d hat beta, the anti-commutator is proportional to p squared. Okay. That's why it has this funny form. But this is now first class, so we can use BRST. Yes? Yeah, so gamma plus, remember, is a matrix. It goes like 1, 0, 0, 0. So, yeah, so S is just SA0. So, yes, so gamma plus S is just S. It's just, if I want to use 16 component notation, then I have to keep track of my gamma pluses. I think I could. So you're just defining S now to be what I used to define gamma plus S. Okay. If you do that, then the index here gets raised because gamma plus takes a lower index to our upper index. And then what you'll find is with your new definition, let's call it S tilde. S tilde alpha with S tilde beta is now equal to gamma plus alpha beta. Okay. Okay, any other? Yes? No. So I didn't tell you yet how space-time supersymmetry acts, but I'll define space-time supersymmetry to act in the same way as I did before. So delta xm is equal to, I'm not going to get the signs right, but and delta theta alpha is equal to epsilon alpha. So you can show that that leaves d alpha invariant. I didn't tell you what delta p is. Delta p alpha is defined such that it cancels this. So it's going to be equal to minus 1/2 p slash epsilon. So d alpha is invariant. Okay, I still have to tell you how I did that too fast, sorry. No, that's right, okay. So that will leave d alpha invariant. It will shift this term because x dot will change by equals, it's going to be 1/2 epsilon gamma theta dot up to signs. But this term p alpha will also transform in such a way that it cancels. Okay, so the action will be space-time supersymmetric. Okay, any other questions? Now, first thing, of course, you want to show is that you haven't changed anything, that this is equal to the original action. So to show that, what I'm going to do is I'm going to show that there's a gauge fixing in which this goes to the original action. So, of course, this is a first-class constraint. So it generates symmetries, local symmetries. So what are the symmetries? So now you have delta theta alpha. So of course the symmetries are generated just by commuting this. This is what we call G alpha. Just commuting this with the variables. So delta theta alpha is just going to be epsilon alpha. So it's not the same. This is global epsilon. This is now local. And then we can compute the other transformation. So you'll find delta S. Now I'm calling it S tilde because I was asked to. So delta S tilde would be the commutator of G alpha with S tilde, right? So this is going to give me 1 over square root of p plus p slash gamma, I think we called it gamma plus. I'm sorry? S tilde was equal to gamma plus S. Okay, so so this is how S tilde transforms. And I missed an epsilon, so there's an epsilon here. So if I put in epsilon alpha, there's an epsilon alpha. And similarly, I can see how X will transform. And then I'm also going to get a transformation of F alpha, right? So I'll get the usual epsilon dot, because it's the Lagrange multiplier. And you'll get an additional term because, remember, this is non-abelian. So G alpha with G beta, we figured that out here. That's equal to gamma plus alpha beta over P plus times P squared. G alpha is the same as D hat alpha, yeah. Well, I can write that here if you like. So that means there's going to be an additional term here, which is going to be related to the Lagrange multiplier. So let's see how this works. So we need delta E is going to be one second, epsilon gamma plus alpha beta F beta P plus. So this transformation of E is necessary to cancel the transformation of this constraint under the symmetry. Okay? So this is the usual term you get from the non-abelian nature of the algebra. Okay, so I think I wrote down the terms. Okay, so there's also delta xm. Delta p will be 0 because p commutes with everything in here. Okay, capital P. Okay, are there any questions? Yes? Yep. So sorry. So this has the local symmetry because this is a first-class constraint. So because this is the first-class constraint, I know that it generates. There's 16 of them, so it generates 16 local symmetries. And okay, now what I'm going to do is I'm going to show that these 16 local symmetries can be used to gauge fix this action to be the same as this action here. Let me just write this action in terms of the S's just so. So the gauge fiction is very simple. In order to get from this action to this, I'm going to use this local symmetry, so this is a function of tau, to gauge theta alpha to 0. I'm sorry? Okay, the change in x. So let's compute it. So d hat alpha is here. D hat alpha is, did I erase d hat alpha? Okay, d hat alpha is here. So it comes from the commutator d hat alpha with x, so that just comes from the p's here. So you get a term equal epsilon times 1/2 gamma m theta. That comes from this term here. And then you get a term from here, which is plus 1 over square root of p plus gamma m s tilde. And finally, you get the term coming from the 1 over square root of p plus. So that'll give you something a bit more complicated, like delta plus m. So it only contributes if x has a minus index, or if it has a plus index down. And then you'll get something like p plus to the 3/2 times p slash s. Okay, so this is the transformation of x. Okay, there's a minus here, I guess. So, I mean, you can read it off just from knowing the commutation relations with p. And there's also a transformation of small p alpha that I didn't write down. So that, of course, comes from anti-commuting with the theta alpha that appears here. Okay. So in fact, that's trivial to compute. That's it just comes from this term in D, so it's going to be p slash epsilon up to a factor of half. Okay, so these are the transformations, the local transformations, which preserve this action. Okay. Now to relate this to this action, what I'm going to do is I'm going to just gauge fix theta equals 0. So that just kills this term. Okay. Now, in that gauge, you don't have any ghosts because the transformation of theta doesn't involve any time derivatives. And this term here is just going to, when you use the equations of motion, is going to just imply that f equals 0 and that p alpha, small p alpha, is determined in terms of the other variables. So what you're going to get is you're just going to get these terms here. So in this gauge fixing, you just return to the original action. So we haven't done anything that changes the physical content. But now there's another gauge fixing where instead of getting rid of the theta, I'm going to get rid of the s's. And in that gauge fixing, you're just going to end up with a covariant set of fields. So that's going to be the punchline. Okay, and then it's with that gauge fixing that we're going to proceed to generalize to the string. Okay. Okay, any questions? Okay, so the next thing to do is to do a gauge fixing as we did before, where we gauge f equals 0 instead of gauging theta equals 0. But we want to do a little better than that, because we want to not just gauge f to 0, we also want to get rid of the s's. So f alpha has 16 components. And what I want to do is I want to gauge fix 11 of those components to 0. So there are actually two ways to do this, two ways to say what I'm going to do. One way to say what you're going to do is you're going to gauge fix all 16 components of f to 0. And that will give you, so let me write it two ways. Gauge fix. That's going to introduce a ghost, which is going to be bosonic with 16 components. I'll put the tilde on the ghost because later we'll see there's another version of the ghost where it only has 11 components of zero. So this is called a pure spinor. I'll tell you what this is in a second. This is an ordinary spinor, 16 components. Oh, Majorana Weil spinor. In this description of the theory, we have Q is equal to lambda tilde alpha times d hat. So just the naive thing we would get from BRST quantization. And then you also get a term coming from the usual mass shell condition, so that'll give you a term Cp squared. And finally, you get a term coming from this non-abelian nature, which gives you a term lambda tilde gamma plus lambda tilde times b divided by p plus. So this comes from the structure constant here. So it's easy to show that q squared equals 0, just using the commutation relations of the constraints. Okay? So we can compute the cohomology. And of course, if you compute the cohomology, you'll get the same answer as you got before. You get super Yang-Mills. Okay? But in this description, things are not quite Lorentz covariant because you have these additional gamma pluses and p pluses. So it's a bit of a mess to compute the cohomology this way. Yeah? In this way of describing it, there's no pure spinor condition yet. This is just an ordinary spinor, but you have d hat. D hat has this somewhat complicated dependence. So this does not solve the problem. It came from gauge fixing F alpha equals 0. So we're doing ordinary BRST quantization. For each Lagrange multiplier, you get a ghost, and that's the ghost. Okay? So this would be just a stupid way of doing BRST quantization starting from this action. You have first class constraints. BRST tells you what to do. That's what you do. The BRST operator is not manifestly Lorentz covariant because there are all these 1 over p pluses and things like that. But you're guaranteed you'll get the right answer because it's equivalent to the original system. Okay? And you can show that you get the right answer. But there's another way to do it, and that's what I'll discuss now and I guess the beginning of the next lecture. Instead of gauge fixing all of 16 components of F to be 0, you can gauge fix just some of them to be 0. In fact, you gauge fix 11 of them to be 0. And in that case, instead of getting an ordinary spinor, you'll get what's called a pure spinor. And I think I'll tell you the answer and I'll tell you what pure spinor is, but I won't finish the problem here. We'll do it in the rest of the afternoon. If you do that, you find that Q has a simple form. We just lambda alpha d alpha with nothing else. So what you find is that if you gauge fix 11 components of F to 0, you still have some 5 components of F's left over. It will turn out those 5 components of F, the equations of motion for them will be related to the S tildes, and also it will be related to this Lagrange multiplier here. So I'll say something about that in the beginning of the afternoon talk. And what you're left with after doing this is just this very simple BRST operator. Now the last thing I'll tell you about before we finish is what this pure spinor is. Okay? So this is the answer, but I haven't yet showed how to go from here to the answer. Okay? Okay, so what is lambda alpha? This is just D. So it's this thing here, which is of course manifestly Lorentz covariant because there's no p pluses or anything. Okay? Okay, so Cartan in the 30s, he described different representations of spinors. And if you have a spinor and you take its product with itself, normally you can do a Fierz decomposition in terms of gamma matrices. And depending on the dimension, you can either get even powers or odd powers of gamma matrices. It turns out that if you're in D dimensions, so first of all, this is obviously symmetric in alpha and beta. So you're only interested in gamma matrices which are symmetrized. And it turns out when D is even, then the gamma matrix which has D over 2 components, so M1 to MD over 2, that's always symmetric. So for example, you're in 4 dimensions, that would be the 2 form, which if I wrote it in terms of Pauli matrices, these are the things you learn which are, it's either self-dual or anti-self-dual. So this would be self-dual and sigma mn would be anti-self-dual. So in 4 dimensions, A and B are just 1 to 2. So this has, it's symmetrized 2 by 2. This has 3 components. So this is the 3 self-dual components. And this would be the 3 anti-self-dual. Okay, so in 4 dimensions, the 2 form, if you have chiral indices is self-dual, anti-chiral indices is anti-self-dual. In any even dimension, it always has that form. The form of half the dimension of D, so this is D over 2, is always symmetric. And then you can have gamma matrices with fewer, and it turns out the next one, which is symmetric, is if you subtract 4 from D over 2. So of course you could also subtract 2, but if you subtract 2, it turns out to be antisymmetric. Okay? So if you subtract 4, it's antisymmetric. If you subtract 8, it's also antisymmetric, etc. So in general, an antisymmetric, a product of 2 spinors will give you something of this form. It'll give you a D over 2 form, a D over 2 minus 4 form, a D over 2 minus 8 form, etc. Okay. Now, in 10 dimensions, of course, this is a 5 form, and this is a 1 form. Okay, this doesn't exist because, of course, it stops when this becomes negative. Now, what Cartan defined to be a pure spinor is a spinor in which all of these components are 0. So pure spinor. So of course for an arbitrary spinor, all of these components will be non-zero, but a pure spinor is special. It's the only non-zero components are the maximal components. So f m1 to md over 2 minus 4, all of these are 0 and also minus 8, etc. So this is a pure spinor. It turns out there's a nice description of pure spinor. It parameterizes the space SO. So if I do a Wick rotation, it parameterizes the space SOD divided by U D over 2. So this is a complex space. So it has D squared, D times D plus 1, D times D minus 1 over 2 divided by D over 2 squared components. So in 10 dimensions, that gives you 45 over 25. It has 45 45 over 25 is 20. So it has 20 real components, which is, of course, 10 complex components. Now, I told you a pure spinor has 11 components. It turns out that if you take the scale factor, so this is a compact space. If you include the scale factor, then you get 11. So So the 10 components, this is what's called a projective pure spinor. So a pure spinor parameterizes this space here. And the projective pure spinor just parameterizes this, so d over u. So a spinor is a representation of the Lorentz group. A fermion is something which is anti-commuting. If you use the spin statistics theorem, then yes, pure spinors, then spinors have to be fermionic in order for the theory to be unitary. So electron, for example, is fermionic as a spinor. A ghost is fermionic, it's not a spinor. A pure spinor is bosonic, but it's a spinor. Okay? So it's important to distinguish in the literature, sometimes people call spinors fermions and fermions spinors, but they're completely independent unless you impose the spin statistics theorem. Okay? So this is bosonic. So I should have said that to start with. Otherwise, of course, this would be 0. Any other questions? Yeah, so this was just because I wrote the coset here. Yeah, sorry. Thanks. Any other questions? Yeah. So this is a compact space. So of course, spinors, in general, lambda alpha, there's nothing that tells you that that the scale part of lambda alpha is fixed. So if you only have product, if you have an equal number of lambdas in the numerator and the denominator, then you can define a projective space. So like when you have a complex projective space, it's everything is equivalent if it's related by a scale transformation. So if you define an equivalence of this type, then lambda this is called a projective pure spinor, and then it in fact parameterizes the space. If you don't identify spinors which of this type, then there's an extra scale factor. Okay. Any other question? Yeah. Yes. Which of course is what you want here because it's going to be a ghost. So it should be bosonic because it's. So normally people define it in odd dimensions by just dimensionally reducing from even. Any other question? So spin statistics theorem tells you that if you try to write a first order action, so for the action for fermion is of the type so in order for this type of action to have positive energy and for chi to have positive norm, this has to be anti-commuting. And similarly, if you try to write an action of this type, second order action, then in order for this to be positive energy and for phi to have positive norm, these have to be commuting. Okay, so that's essentially the proof of this spin statistics theorem. But if you don't care if the energy is positive or you don't care if it has positive norm, this could be commuting or anti-commuting. So the fact that chi has a spinor index just tells you how it transforms under the Lorentz group. So as we already saw, if you have ghosts don't satisfy positive energy. I mean, so you have B, what do I want to say? So in Yang-Mills, the ghost action is of this form, but these are fermionic. So. Okay, any other questions? SOD, is it D times D plus 1? What was the question? I think this is formula is right, but okay. Any other questions? Okay, so in the afternoon, I'll start by saying more what this pure spinor is. So I'll give you an explicit description in terms of these gamma matrices that I described earlier. So I'll essentially solve this constraint. So just to tell you, in 10 dimensions, this constraint implies, of course, that lambda gamma m lambda equals 0. So this is the definition in 10 dimensions just because you have to kill this component here, which is just gamma m. Now, this constraint, of course, tells you that not all of the components of lambda are independent. And we'll see exactly how this constraint reduces these 16 components to these 11. Okay, so they'll have to wait until the afternoon. Okay, so I'll stop there.